Yeah, Lee, it's underneath the ground near a volcano, specifically the Newberry Volcano. I spoke to the company that's been testing at the site for over a decade, and they tell me their latest study is very promising.
The Newberry Volcano, long considered a relatively quiet geological feature in Central Oregon, has recently exhibited surprising and intriguing activity. Satellite imagery captured over the past few months has revealed a slow but measurable ground uplift, a phenomenon often associated with subterranean magma movement. This unexpected shift in Newberry's behavior has captivated volcanologists and geologists alike, not only because of the implications for regional geologic activity, but also because of what it might signal about the volcano's future. Before we start, smash the like and subscribe buttons for more updates. The first hints of this development emerged through satellite-based radar interferometry, a powerful tool that detects minute changes in the Earth's surface. These images showed subtle but consistent inflation centered around the caldera, the large depression at the summit of the volcano. Over the past several decades, Newberry has been monitored for volcanic unrest, but this latest episode marks a distinct and unusual event. The caldera's floor has been rising steadily, suggesting a gradual accumulation of magma beneath the surface. Though the uplift is modest in scale, just a few centimeters, it is geologically significant. In volcanic systems, even small deformations can be early signs of subterranean pressure changes. Newberry Volcano is a complex shield volcano, spanning more than 1,200 square miles, making it one of the largest volcanoes in the United States. It is known for its broad profile and diverse geological features, including lava flows, cinder cones, and the striking twin crater lakes, East Lake and Paulina Lake, that fill part of the caldera. While the volcano has erupted numerous times in the past, with its last known eruption occurring about 1,300 years ago, it has largely remained dormant in recorded history. The recent uplift, however, has shifted scientific focus back to this immense and complex geological structure. The implications of the observed uplift are far-reaching. Uplift events often occur when magma intrudes into the crust, but doesn't necessarily result in an eruption. Still, they are important indicators of the internal dynamics of a volcano. The satellite data has shown that the uplift is centered in a zone historically considered to be a focal point of past volcanic activity. This spatial alignment adds weight to the theory that magma is accumulating again at shallow depths, likely between 3 to 6 kilometers beneath the surface. This is a critical depth range, where the crust is brittle enough to fracture under pressure, potentially allowing magma to ascend further toward the surface. Such deformation is not just a physical change, it alters the internal stress regime of the volcano. As the ground rises, faults can shift, pressure can redistribute, and new fractures can form. These changes create potential pathways for magma, altering the probability of future eruptive activity. Scientists monitor not only the uplift itself, but also associated seismicity, gas emissions, and thermal anomalies, all of which can offer additional clues. So far, the activity at Newberry has not been accompanied by significant increases in seismicity or gas emissions, which is somewhat reassuring. However, the absence of such signs doesn't negate the seriousness of the uplift, especially when it persists over weeks or months. The phenomenon has also reignited discussions about the long-term monitoring and risk assessment of volcanic regions in the Pacific Northwest. While Mount St. Helens and Mount Rainier frequently dominate headlines and preparedness strategies due to their explosive histories and proximity to population centers, Newberry has often been treated as a secondary concern. This latest event challenges that perception, underlining the importance of comprehensive monitoring systems that include even those volcanoes previously deemed low risk. The geological history of Newberry reveals a capacity for varied eruptive styles, from quiet lava flows to explosive ash emissions, and understanding what may come next requires intense scrutiny and updated models. Beyond the immediate geological interest, the uplift at Newberry has broader scientific significance. It presents a rare opportunity to observe a reawakening process from the earliest stages. Many volcanic eruptions around the world are preceded by ground deformation, but such phenomena are often detected only shortly before an eruption occurs. In contrast, the changes at Newberry are occurring gradually, offering scientists time to study the pre-eruptive signals in real time. This makes the volcano a natural laboratory for understanding the intricate dance of magmatic systems deep within the Earth. One of the most fascinating aspects of this ground deformation is how it fits into the broader geologic framework of the Cascade Range. Unlike the iconic stratovolcanoes that form the backbone of the range, towering peaks like Mount Hood and Mount Adams, Newberry's structure is more complex and expansive. It straddles the boundary between the Cascades and the high lava plains, a region marked by deep tectonic rifts and extensive basaltic flows. This unique setting contributes to its unusual volcanic character. It is capable of producing both basaltic lava flows typical of shield volcanoes and more explosive rhyolitic eruptions. The current uplift raises questions about what type of magma is involved, information that could drastically affect the forecast of future volcanic behavior. Geophysical models are currently being refined to determine the size, shape, and location of the magma body responsible for the uplift. These models use data from satellites, ground-based GPS stations, and other remote sensing tools to create three-dimensional images of the subsurface. Early indications suggest that the inflation source is shallow and relatively small, but persistent. This persistence suggests a continuous or episodic supply of magma from deeper sources, which could lead to further deformation or even shallow magma intrusion events in the future. The evolution of this system over the coming months will be critical in determining the level of volcanic hazard posed. Meanwhile, scientists are working to communicate these developments to local communities and stakeholders without inciting unnecessary alarm. The Oregon Volcano Observatory has increased its level of scrutiny, deploying additional instruments and increasing data analysis frequency. Public information campaigns are emphasizing the scientific nature of the uplift and the importance of preparedness, regardless of whether an eruption is imminent. It's a delicate balance, conveying the importance of these changes without overstating the risks. Yet the message is clear. Newberry Volcano is not as dormant as once believed. What makes the current situation particularly compelling is how it contrasts with the volcano's external appearance. From the ground, Newberry remains serene. Its pine-covered slopes and glassy crater lakes draw campers, hikers, and anglers each summer. There's little at first glance to suggest any kind of internal turmoil. But beneath this calm facade, the Earth is shifting, slowly and methodically. It's a reminder that volcanic activity doesn't always announce itself with dramatic explosions or violent earthquakes. Sometimes it begins with a quiet upward bulge, silent, steady, and almost imperceptible to the casual observer. The story unfolding at Newberry is also a stark illustration of the power of modern remote sensing technologies. In previous generations, such subtle signs of volcanic unrest might have gone unnoticed until much later in the reawakening process. Today, satellite constellations continuously scan the globe, detecting changes in topography with astonishing precision. This technological capability has revolutionized volcanology, allowing researchers to detect and analyze precursors to volcanic activity at a global scale. In Newberry's case, the early detection of uplift provides a rare window of opportunity to prepare, study, and adapt. Importantly, the uplift does not occur in isolation. It is part of a larger pattern of geologic flux observed across the Pacific Northwest in recent years. Small tremor swarms, crustal deformation, and heat anomalies have been recorded at various locations, prompting a re-evaluation of the tectonic and magmatic systems that define the region. While not all such events lead to eruptions, they do contribute to a growing recognition of the dynamic nature of the Earth's crust in this part of North America. Newberry's activity thus becomes one chapter in a broader narrative of geological awakening. Even as scientists continue to track the rise of the caldera, questions abound. How long will the uplift continue? Will it plateau, reverse, or accelerate? Could this be the beginning of a new eruptive cycle? Or will the magma simply stall and solidify beneath the surface, as has likely happened before? Each possibility carries its own set of scientific and practical implications. If the magma does begin to ascend further, changes in gas emissions or seismicity may follow. If not, the uplift could stabilize without further incident, providing a valuable case study in non-eruptive magmatic intrusions. Regardless of the outcome, the Newberry uplift highlights the ever-present potential for change in Earth's volcanic systems. It serves as a vivid reminder that even the quietest volcanoes can stir, driven by forces that are invisible to the naked eye but unmistakable through scientific observation. These events challenge assumptions, prompt new questions, and fuel the advancement of knowledge. They also reinforce the need for vigilance in regions shaped by volcanic forces, no matter how tranquil those landscapes might appear. In the months ahead, researchers will continue to analyze new satellite passes, ground-based measurements, and thermal imagery to track the situation. Each dataset adds another layer to the growing understanding of what is transpiring beneath Newberry. Collaborative efforts between federal, state, and academic institutions are ensuring a comprehensive response, pooling expertise from across the geoscience community. These efforts not only help in deciphering the present uplift, but also contribute to the long-term safety and resilience of communities living near volcanic terrain. While the initial discovery of uplift at Newberry Volcano set off a wave of scientific excitement, the unfolding developments since then have only deepened interest in the evolving dynamics beneath this vast shield volcano. What makes the current phase particularly compelling is the nuanced complexity it introduces. This is not a case of obvious precursors or textbook precursory signs, but a situation layered with subtle, sometimes contradictory signals that push the boundaries of volcanic interpretation and demand innovative approaches in both analysis and surveillance. One of the more intricate aspects of this ongoing uplift is how it interacts with the existing geothermal systems inside the Newberry caldera. The volcano is home to one of the most active geothermal fields in the Pacific Northwest, long explored for its potential as a sustainable energy source. The hydrothermal system here includes hot springs, fumaroles, and a substantial thermal gradient in the surrounding rock. As magma slowly intrudes at depth, it may be influencing this system in unexpected ways, altering subsurface fluid movement, changing water chemistry, and modifying heat distribution. These changes are currently being investigated through geochemical sampling and heat flux modeling. Subtle shifts in geothermal flow could serve as indirect indicators of increasing magmatic pressure, or even reflect new fracturing of rock caused by inflation, offering another way to infer what's occurring beneath the surface. The challenge lies in separating natural geothermal variability from changes driven by magmatic intrusion. The long-standing thermal activity at Newberry has created a noisy background signal. To isolate the volcanic component, scientists are deploying time series analysis and cross-referencing multiple data streams. Isotope analysis of gas samples, for example, might reveal the emergence of deep magmatic gases like helium-3, an unmistakable tracer of mantle-derived material that would provide strong evidence for active magma replenishment. While monitoring techniques are becoming increasingly advanced, the growing volume of data requires more sophisticated interpretation methods. Artificial intelligence and machine learning models are being brought into the fold, trained to detect patterns that human analysts might miss. These systems analyze terabytes of satellite imagery, seismic records, and GPS displacement data, comparing present activity with historical analogs not only from Newberry but also from shield volcanoes around the world. The goal is to build predictive algorithms capable of forecasting the likelihood of escalation, an eruptive threshold that remains both elusive and critical to define. Geologically, the Newberry system is thought to rest atop a complex faulted crustal region, influenced by both extensional and compressional forces. This dual tectonic identity complicates magma storage and transport. Fault lines in and around the caldera act as potential conduits, or barriers to magma movement. New geophysical surveys are underway to map these faults more precisely, especially those that intersect areas of active uplift. Magnetotelluric data, collected by placing sensors in the ground to measure natural variations in electric and magnetic fields, are revealing zones of low resistivity, consistent with partial melt or hydrothermally altered rock. These zones help delineate where magma may be pooling and what directions it could potentially migrate. As scientists probe deeper into the volcano's anatomy, new structural models are emerging. It appears that the current deformation may be influenced by a long-lived magma reservoir that has existed beneath the caldera for thousands of years. This reservoir, likely complex and multi-tiered, may be reactivating from below due to influxes of hotter, more primitive magma rising from the mantle. The mixing of new and old magma introduces additional volatility into the system. When fresh magma intrudes into a cooler, partially solidified reservoir, it can destabilize the system, triggering increases in gas release, crystal formation, and pressure buildup. These internal dynamics are now central to understanding what could come next. Environmental sensors placed throughout the caldera are now delivering real-time feedback on surface temperatures, microseismicity, and hydrological changes. Interestingly, there has been a slight but measurable change in lake levels at Paulina and East Lakes, both of which sit inside the caldera and are sensitive to underground movement. These fluctuations are being interpreted cautiously. They may result from minor shifts in the lake beds due to deformation or from subtle changes in the underground plumbing systems that feed the lakes. In either case, the linkage between surface water systems and deep magmatic activity is an area of ongoing exploration, offering yet another lens through which to monitor the volcano's state. The human dimension of the Newberry uplift cannot be overlooked. Although the area is sparsely populated compared to more urbanized regions near other volcanoes, there are communities, recreational facilities, and a growing number of renewable energy projects in the vicinity. The possibility of future unrest, even if distant, has prompted renewed assessments of infrastructure vulnerability. Evacuation planning, risk communication strategies, and public awareness initiatives are being re-examined. Importantly, there is a coordinated effort between federal geological agencies and local governments to ensure that response plans are proportionate to the evolving situation without causing panic. The local Native American tribes, who have deep cultural and historical ties to the land around Newberry, are also being engaged in this process. Their oral histories and traditional knowledge may contain valuable insights into past behavior of the volcano that predates written records. Integrating these narratives with modern geological data represents a broader, more inclusive approach to volcanic hazard understanding. The land itself carries memory, and tapping into these indigenous perspectives adds both cultural depth and temporal breadth to the monitoring effort. Another component gaining attention is the ecological impact of even small volcanic changes. The caldera is home to a unique range of flora and fauna, adapted to its distinct high-altitude volcanic environment. Uplift and subsurface heating can alter soil composition, water pH, and local temperature regimes, changes that may affect plant communities and aquatic ecosystems. Researchers in biogeosciences are conducting baseline studies to identify any early biological responses to these geological shifts. These ecosystems, sensitive and self-contained, may act as living indicators of subterranean change. In terms of regional implications, Newberry's unexpected activity has sparked comparative studies with other shield volcanoes across the globe, particularly those in similar tectonic settings. From Iceland's Bardarbunga to Hawaii's Mauna Loa, scientists are finding parallels and contrasts that help frame Newberry's behavior in a global context. Each volcano has its own fingerprint, but common themes, like caldera resurgence, mixed magma systems, and complex fault interactions, provide valuable analogs. These global case studies offer both cautionary tales and analytical frameworks that may be applicable as Newberry's story continues to unfold. Meanwhile, long-term datasets collected over decades at Newberry are being reanalyzed with fresh eyes. Archival seismic records, early thermal imagery, and previous ground deformation surveys are now being reviewed to determine if similar patterns occurred in the past. This retrospective analysis can reveal slow-building trends that were previously overlooked. For instance, there is evidence of minor uplift episodes in the 1990s that went largely unnoticed at the time due to limited resolution. When placed in context with today's activity, these older signals could provide a timeline of volcanic dormancy, punctuated by brief but meaningful pulses of unrest. One of the most valuable tools in interpreting such slow-moving volcanic processes is petrology, the study of the rocks produced by the volcano. Recent fieldwork has focused on collecting and analyzing samples from older lava flows and tephra layers within the caldera. These samples are subjected to detailed mineralogical and chemical testing, revealing not only the composition of past eruptions, but also the conditions under which the magma crystallized. By understanding the pressure, temperature, and volatile content of these ancient magmas, geologists can infer how similar the current intrusion might be. If today's magma shows chemical similarities to those that preceded explosive activity in the past, it could shift the risk profile considerably. The geodynamic forces at work beneath Newberry also open up broader scientific questions about crustal evolution and magmatic cycling in continental settings. Unlike oceanic shield volcanoes, which typically involve simple basaltic plumbing systems, continental shields like Newberry interact with older, thicker, and more compositionally varied crust. This adds complexity to every stage of magma evolution, from mantle melting to crustal storage to eruption. Understanding this process contributes not only to hazard mitigation, but also to fundamental Earth science, offering insights into how continents are reshaped over geologic time through magmatic addition and tectonic reworking. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on Newberry Volcano's ground rising? Will it erupt soon? We want to hear from you. Thank you for watching and see you next time.